Anything? Yeah. Good. Okay, so welcome to the Quantum QBC Seminar, the first one of 2026. I wish you a good break. So today we are very happy to have Dr. James Brown from qBraid as our speaker. So James is a research scientist and software developer at qBraid. He develops and implements methods to calculate properties of materials using both classical and quantum-inspired algorithms. So he has published a lot of work about the methods to calculate a broad range of material properties, including molecular vibration, vibronic dynamics, and electronic structures. So he is now going to tell us about the recent developments today. Thank you, James.
Thank you for the kind introduction.
Thank you. Yes, I will.
All right, so this is just a very brief introduction to qBraid as a company. This is our main value that we provide is we take users from beginners to production ready in 4 steps. So there's qBook, qBraid Lab, qBraid SDK, and qBraid Runtime. I will have a demo of the platform after talking about the research we do at the company as well. So the first topic that I'm going to talk about is classic reservoir computing. So to start off, I'm going to start with what classical reservoir computing is. So in this case, you have some input signal, which could be previous time steps or other information that you feed into some reservoir that evolves in time. This is not a trained reservoir. This is just some dynamical system that depends on these input parameters you're feeding in. And then if you have something you observe from the dynamical reservoir, this can be many different things that you can use as a reservoir. Often it's just matrix multiplication, as I'll show on the next slide, but there's some other interesting ones like dynamical chemical reactions, where you read out, say, the color of the system and use that as a reservoir. So it's a very general method. After you read out those observables, you train on the output signal a linear regression, and you try and predict whatever system you are actually interested in. So this is, as I was mentioning, the matrix multiplication version. So you've got your input signal U on the left. This is fed in with some W in matrix, which just transforms it into the same shape as your reservoir. And then you have some internal evolving X variable. And from that, you read out, in this case, it's the full state X. And then you only train this linear regression W out to try and predict the system you're actually interested in, which is Y. When you look at the matrix, in this case W, the eigenvalues of that determine whether it's trying to remember long-term dynamics or short-term dynamics. So in this case, you can tune your matrix so that if you're only interested in, say, long-time dynamics, you push all your eigenvalues to the outside area. So you are not looking at any short-term dynamics. You don't have any eigenvalues greater than 1 because otherwise it would explode. Your vector X would explode. So that is how you can define a reservoir that only looks at certain dynamical, the time evolution sort of processes. Another way you can also do this is a recently developed onion design where you just have a block diagonal W matrix where each of those blocks has represents a different part of the annular spectrum. So what this does is it possibly makes training easier, but it certainly increases the explainability of what your reservoir is doing. So you can see at different points in the time series you're trying to predict what the expected outcome should be. So moving on to quantum reservoir computing. So this is where you replace your reservoir with a quantum computer. So this is a excellent paper out of Quera where they use their neutral atom platform to both try and do image prediction and also time series prediction. So they feed in some sort of input signal into their quantum reservoir. In this case, they're just evolving their analog Rydberg Hamiltonian, and then they're measuring the Z and ZZ expectation values for all their qubits. And from that, they use linear regression to try and predict what that input signal was, in this case, a horse, or the future time series output. A different quantum reservoir that one can use is a digital quantum reservoir. So this is where you design a circuit that, once again, you feed in these input parameters. In this case, you only have one input parameter. That's A in the top left there. And the other ones are Z expectation values from the previous time step. So this is the sort of the analogous process where these are the X from before, and you feed those back into the circuit, these parameterized circuits. But once again, the key point here is that you are not training this reservoir, so there's no barren plateaus. You just have to be careful in how you design the circuit so that it can be expressive enough to explain the dynamics you're looking at. So in this paper, they showed that you could predict these chaotic systems fairly well with this quantum reservoir, which here is 8 qubits. And I think that's the only one size of system they looked at. So what we applied this to was for material degradation in aerospace. So the experimental data that we looked at is this testing system here. So you put samples into this chamber and expose it over 14 days to different atmospheric conditions. So relative humidity and temperature are the main ones we were looking at. And you can see that they cycle from simulating sort of a day to night sort of process. So there's 4 different boxes. They have different gels on top, or if they're in water, or their holes are covered, and these have different evolutions of the degradation process that is accelerated in this case. So here, every 12 hour or every day, they open the box, take a picture, and then quickly resume the cycling process to obtain the information needed to characterize the degradation that is occurring. So this is what the degradation looks like. So you start from just an etch on your system at 0 hours. And as you can see, the corrosion continues throughout the 14 days, over 2 weeks. So there's how the property we're trying to predict is a spectral decomposition. So they take this picture and you can see there's three regions: pitting, tarnishing, and then an unaffected region. And we are going to try and predict these properties, these spectral properties of the system as we move along. And this is what the time series looks like. So the middle region tarnishing on the left there, and on the right, you can see pitting. We are going to look at pitting because it is more difficult to predict. There's a bit more, it's a bit more non-deterministic depending on the box you're looking at. So the problem is, given a set of tarnishing, pitting observations, and future climate conditions, so the only ones we're allowed to use are temperature and humidity. They did measure conductance, as you can see in the table there, but we're not going to use that because you'd have to look at the, actually look at the system, and if you're there, you could just do the measurements anyway. So we're trying to predict what will happen without looking at or actually touching the sample. So what we developed was a gate-based design similar to the one I spoke about earlier, where you feed back in these observables back into the circuit. But unlike this one, ours looks like this. So we've got that same feedback parameter on the top left there. And then these observables Y0, Y1, and Y2 are the arc coasts of your Z expectation value for each qubit. If you look at this feedback parameter, so that's the coefficient in front of the top left for the input signal. There's a region where this is good. So stable is not quite right. What you want is the edge of chaos so that it has the most expressiveness for the circuit, and should be able to predict a wide variety of systems. So for here, for pitting, the model that we definitely need to beat is the simple classical model. So this is taking the average value of the training set. So in this case, it's 10 of the 12 evolutions, and using that to predict the next evolution. So this doesn't take any information about the specific box time evolution. It just it just guesses given the average of previous versions. So here, if we did one model for all the different boxes, you can see that we need to go up to around 8 qubits to start beating this simple model. And it kind of plateaus after that. So humidity and temperature are probably not enough to describe the intricacies of each time evolution. But one interesting thing is when you look at this evolution, there's two hyperparameters in this, the coefficient in front of your input and the coefficient in front of your feedback. So you can do a 2D surface. So this is the parameter landscape. And you can see that when you're at 6 qubits, there's no choice of hyperparameters that beats the simple model, which is the flat plane there. When you go up to 9 qubits, there are a couple little islands that show up that do beat the simple model. So if you choose those, then it should work for many different systems. And if you go to 12 qubits, then you can see that this island grows a bit. So there's extra expressiveness that comes from adding more qubits to your system. Previously, we trained all the boxes with one model. If you do train a different model for each of the boxes, then and using the same hyperparameter, then you can far surpass the simple model's R-squared value. Just because just by not assuming that the only appropriate parameters are the humidity and temperature. Next, we did resolve from classical reservoir computing that there's this tuning you can do for eigenvalues. And we can actually do the same thing with quantum reservoir computing. So if you had no measurements in your circuit, so if you just did unitary dynamics, then all your eigenvalues have absolute value 1, and it would just, this is for a 5-qubit system. You can see that the eigenvalues are on the unit circle. Another thing that you could possibly use is noise. So this will make the dynamics non-unitary, but this is hard to control because this would depend on your hardware. It is plausible that you could have hardware that would define this very well, but we decided to go a different route. There is other work showing that you can tune your hardware noise to have a better reservoir. So for this, 4 measurements below, these are the M are the measurements, then you can tune the eigenvalues of your evolution. So on the left is increasing your feedback parameter coefficient. You can see that you can tune values that way, and that's the approach to use. If you add more mid-circuit measurements, you can also change the non-unitarity of your dynamics. So here we decided that we should combine classical and quantum reservoirs. So that's what this matrix is saying. There's one classical reservoir, and then we had multiple quantum reservoirs with different eigenvalues of the evolution. And we use that to predict the dynamics of this material degradation. And as you can see from here, the purple triangle is this combined classical quantum reservoir, and it has the best R squared for this system. So by the main thing we learned from this work is that you can design a quantum reservoir to describe long-term and short-term dynamics, and using that, you can obtain better results than you could with either classical or just quantum reservoirs. So the paper and code are given here, but I can certainly provide these slides at the end. So the next research topic that we have been working on is the generalized superfast encoding. When you have a chemistry Hamiltonian written in terms of fermionic raising and lowering operators on the top left there, you can, in order to use it on a quantum computer, this needs to be mapped to qubit operators. This can be done using standard mappings. Another way to do it is to convert these fermionic operators, these A and A dagger, to Majorana operators, and the correspondence between them is given on the right. And then your qubit Hamiltonian is defined in terms of what you call these edge and vertex operators, which are products of these Majoranas. So standard mappings like Jordan-Wigner and Bravyi-Kitaev, they work in fermionic space where you have these dots representing your fermionic modes. Here, we're going to define an interaction graph. So this is if there's an interaction or a hopping term between two modes, then we put an edge there between the fermionic mode vertices. And for the generalized superfast encoding, instead of placing a qubit on a mode, we place qubits on these lines or edges here. And then the vertex and edge operators are defined using local Majoranas, which are placed which are defined using these qubits that we placed on these edges. Of course, once you add these extra qubits, more than modes, what you get is you get some redundancy in your system, and from this you can define stabilizers. So if you go around a loop, so you interact or you hop between each of these modes and then you come back to the same spot, then nothing should have happened. So this is a redundancy of the system, and this can be used to do error correction or error mitigation. So the choice of those local Majoranas between these fermionic modes defines the properties of your generalized superfast encoding. So here, we're going to use a simple, this choice of modes here, defined in the middle. So it's just cyclic permutations of these two base Majoranas. And then this works for graph of d over 2, or the degree, the code distance is d over 2. So if you connect these appropriately, and this is a non-trivial task, but when you do this, what you get is an increasing distance code, but with your stabilizers, they're always weight 6. So you don't increase the weight of your stabilizers, which means they don't get harder to measure. There's just more of them. And the error correcting properties increase. Another useful thing that came out of choosing the Majoranas this way is that when you hop between next nearest neighbors, you only have the same overhead as your Jordan-Wigner encoding, so a single Z operation, even though you have this extra error correcting or error mitigating properties. And the benefit that you get from this is that now you can parallelize Trotter operations. So in this case, you've that Hamiltonian on the top left there, using Jordan-Wigner. You have, I think it was depth 27 to do a first order Trotterization of it. Whereas here we used 3 times as many qubits because it's a distance 3 code. But the total circuit depth is actually 24 instead of 27, just because you can now perform some Trotter operations in parallel that you could not using Jordan-Wigner. We also showed the error mitigation is effective on hardware. So this was an experiment of an orbital rotation circuit using on IBM Kingston, and you could see that with using these stabilizer measurements, you rejected about 60% of your shots. But what you got out of that is the root mean square of the state you obtained was about twice as good as with Jordan-Wigner, even though you used about twice as many gates. So that's useful as mitigation. This is another technique we're looking at, which is a lookup, trying to move this towards fault tolerance. So this is, as I said, as you increase the code distance, your logical error rate should decrease. So this is the depolarizing error probability and the logical error rate. This is a standard quantum memory experiment. But the problem when you do these Trotter circuits is that there's hook errors. So when you have CNOT gates between codes in your code space, or qubits in your code space, then a single qubit error can propagate to a multi-qubit error, which might be undetectable depending on the distance of your code. So there was recent work by Narayan and Rangaswamy from University of Arizona that suggested that the Trotter circuit itself can be fault tolerant. But this does not correct the hook errors. So what we tried to do was to borrow this Clifford noise reduction circuitry which was developed from IonQ, and try and decrease the problematic hook errors for a trotterization. So this is the standard Trotter circuit that I showed earlier, where you've got some Clifford gates, and then in the middle, you in general have a non-Clifford circuit, the single RZ rotations, and then you have more Clifford gates. So the process here is you do Clifford noise reduction, physical RZ rotations, and then Clifford noise reduction, and hope that you can have fewer errors. So when we first attempted this, although the rate of undetectable errors, so if an error did occur, it was less likely to be undetected. There were so many more errors that it didn't decrease the number of undetectable errors. So we moved on to a different circuit, and so a larger one, which is shown to be better for this Clifford noise reduction. And we also implemented better stabilizer measurements. So I didn't mention this earlier, but how Clifford noise reduction works is you've got your state on the top left there. You prepare these bell pairs and then apply your Clifford circuit you care about. So in this case, it's the CNOT ladders. And then you perform stabilizer measurement. That's the control P there. And if that is not satisfied, then you restart your preparation process, so the C and the control P part, until that is satisfied. And then only after that, you do these CNOT gates between your state and this resource state. And then you apply a operation Q depending on the output. But what we did was we did this fault tolerant stabilizer measurement, or Shor style. And from that, you got, you do at least, we do need to get better statistics on this, but at least appears that you're not doing worse anymore with this. So we're continuing to work on this, but we will hopefully be able to start having some fault tolerant simulations with GSE. So the last research topic I'm going to talk about before moving on to the qBraid platform itself, demonstration of that, is this Hamiltonian derived Clifford transformation. So Clifford gates, which I alluded to earlier, but they are any circuit that can be decomposed into only these three operations. So the Hadamard, the S gate, and the CNOT gate. And these transform polys to polys. So if you apply a general circuit, if you perform that operation on a poly word, it will in general create more poly words. But if it's these Clifford gates, then it only maps one poly to one poly. So these are efficiently simulatable. So there are processes you can use to simplify circuits. So this is, you've got some starting state V0, which in this case is a single layer of X gates for, say, Jordan-Wigner. And then you've got these Trotter circuits. And you can look at this. In this case, in the middle there, they swapped the H and X control X gate. And from that, what you obtain is this C1, which can then be pushed through all your other Trotter steps. And from that, you've now converted from 0 to 1. You've taken one of those Trotter circuits and converted it to a single qubit rotation and also changed your Hamiltonian. So you can repeat this process again, and in this case, they reduced their much larger circuit to 3 single qubit layers, rotations, and a different operator that has been modified 3 times in this case. So what we noticed is that from Qubit Coupled Cluster, this is a way to generate a reasonable variational quantum ansatz. And from a qubit Hamiltonian, you look at each Hamiltonian element. So as an example, here we have x0, z2, z3, x6, z8. The flip indices are ones with x or y on it, so it's 0 and 6. So then you flip one of those to either x or y, whatever one it isn't. And from that, you generate a candidate operation, which you would then put into a Trotter circuit generally. And from this, you get a reasonable ansatz. What we noticed is that if you put this into these binary matrices, so the columns here are flip indices. So for example, the first column on the left there, its flip indices are 1, 2, 5, and 6 for this 8-qubit system. And these are different generators. If you perform this Gaussian elimination over binary fields, after that, you get on the right, you see that now 3 qubits have no indices. Those are ones that can be tapered. They do not contribute to the Hamiltonian at all after this transformation. And you now have single flip indices or single RY terms in columns 1, 2, 3, 4, and 6 on the right. So this can be defined as a CNOT only transformation. And now your ansatz is given as a single layer of RY gates. So instead of looking at the circuit and seeing if you can simplify, it's a simple generate your qubit coupled cluster ansatz and define the CNOT only transformation. And as you can see here, the qubit coupled cluster CP, it's canonical polyadic form. It gets better accuracy than MP2 for this H4 on a minimal basis. Obviously, it doesn't get the full CI accuracy, but it does pretty well. When you use the new Hamiltonian in DMRG, you can see that on the left, for a given bond dimension, the accuracy is increased quite a bit because you removed a bunch of the entanglement between the qubits compared to a tapered Jordan-Wigner, which is shown on the right there. The entanglement is about halved between each of the qubits in your system. You can also repeat this transformation, and what you get is a single RY layer and then a bunch of CNOT gates in between. And this gives you sort of a hardware efficient ansatz that you can also guess the parameters on. So that's the blue squares there, or blue X's there. And compared to standard hardware efficient ansatz, which does pretty poorly, this Hamiltonian derived hardware efficient ansatz does much better for this lithium hydride system. So the paper and code are coming soon. I'm just going to highlight a couple other projects. This is QuantaBind, which is, you can look at the paper there. And this is qubit encodings for dipolar planar rotors, which was work with Pianois at University of Waterloo. All right, so that's it for the research part. I think in the interest of time, I'm gonna do a demo of the platform now. So this is qBraid. So this is the page here. If you were running a course, then you'd have organizations, which you could add users to. These are all the devices from which you can submit quantum jobs to, and we're going to submit one to a quantum computer in this demonstration here. So IQM, Rigetti, quantum jobs. These are different ones that I have submitted, so you can see that here. So this was a 2-qubit Bell state, which is the one I will do. We do lots of hackathons, so we are a platform that people can easily start coding quickly, and I'll once again show that. Courses is another big thing that we do. So for example, our introductory cubes beginner course. So this is, you could use with students or just to learn yourself. So this is a bunch of information. Here we can have some videos looking at how you can learn about all the math. And one of the best parts is you can have these functional codes while you learn. So there was learning about vectors. Maybe we can get to circuits. So here. And then, of course, you can change the gates. So gate. And so these are fully interactive ways that you can learn about quantum computing. Composer is the more, you can look at block spheres. So I'll generate a GHC, 2-qubit GHC gate, and you can look at the block representations. Sorry, that was wrong. Yeah. So that is another cool feature that we have. So back to the main platform, I already have an instance running. So this is lab here. Now I'm going to show how easy it is to generate or to run on a quantum computer. So if you go to qBraid lab demo, you might see these on other platforms as well, but here is a launch on qBraid button. So this will copy this code, this GitHub repository into qBraid lab here. So it should show up soon. Right, so it should be here now. There it is, 4 seconds ago. So we can go into qBraid lab, quantum jobs. So this is where you can develop quantum applications quickly and deploy on GPUs and QPUs. So it's going to install a couple things. So here, I'm using this smallest system, but there's access to GPUs as well if you need more compute power. This is, so I'm going to continue running this notebook. And as we go, you can see that there we have this environments. So here I'm using default, which has essentially nothing installed, but there are many other environments. So if you're working with GPUs, there's a qBraid environment, and this is the latest one. So I can get that to install in the background and then use it. Or Qiskit. So this has continued. All right, so this will tell me how many credits. I have a fair amount. That's a Bell state that we're going to run. So this is going to run on AWS state vector 1. So this should now show up in my jobs when I run it. It's initializing, as you can see. And then when the results come, it'll show up here. While that's happening, I'm going to show you the different devices. So we can see that we had a perfect system, so only 1, 1, and 0, 0 returned. I'm going to use Anka1 to run this job again. So I will change this device here. And then that should now show up in the jobs. Once I press run. All right, so that one has been submitted to Anka3, which is the newest Rigetti device. And we will see when the results come back. All right, so as you can see, as this was run on a real quantum computer, there is noise here. But yeah, any one of you could easily sign up. Signing up for an account is free, and you can run as quickly as I did just there on a real quantum computer. So that is all I have, but thank you for your attention.
Okay, thanks for an interesting talk. It seems to be very exciting to try out this qBraid. Is it free for everyone right now, or is it just
it's free to try. Running on a quantum computer will cost credits, but yeah, you can pay a subscription to get more advanced features.
Okay, any question from the audience or from the Zoom side? Maybe I will start with one. So when you talk about that fermions to qubit code, and then you say that you can embed some quantum error correction capabilities inside. So what kind of error model you're considering? Is that just depolarization model, or you can actually change it to other type of model as well?
At this point, it was just a depolarization model, just for simplicity, and we could study the scaling using STIM or a Clifford simulator. But as you can see on the real hardware, it does work in practice as well. So that was for a very small error distance, just distance 2, so only error detecting. But
yeah, okay.
We hope to study bigger systems.
Yeah, I'm thinking maybe most of the physical platforms, the defacing is more an issue. So.
Oh, okay. Yeah. That's good to know. Thank you.
Yeah. The question?
Yeah, I have a question. Yeah, first of all, thank you, James, for the nice talk. And I was wondering if you because at some point you were involved in developing Tangelo, as far as I know. I was wondering if you know if this is still like being actively developed, or if you can like share any insights there, because I had the feeling it unfortunately like stopped a bit.
Yes, unfortunately, it does appear. I don't think they're actively developing it. They will respond to issues, but yeah, I don't have more information. But
okay.
Yeah, I may fork it and start developing it too, or just contribute. But
okay, you think they would still like if you, for example, like implement a feature, people might still like
they're still
review it and merge it.
Yeah, they still do that, but they are not actively contributing anymore, as far as I know.
Okay, sounds good. Thank you.
Questions? So from the educational perspective, So we think that's the stuff you guys are working on are very cool. So if a students want to say do an internship or join your company, so is there any opportunity available right now?
So we do hire interns. We have a few right now, graduate student level interns. Occasionally in the summer, we do have upper level undergraduates. But yeah, you should just reach out to us, one of us, if you're interested in an internship, and we'll see if there's a fit.
Great. So students, take take a look at that. Okay, any more questions? Okay, yep, go ahead.
Does this platform enable you to compare different benefits from different quantum computers, or what they might be more advantages, what might be more advantages of different operations?
Sorry, I missed kind of the middle there.
Yeah, you can come out. Yeah, we'll closer to the mic. The mic is, yeah, the mic is here.
Does this does this platform allow you to compare different quantum computers and see which different operations are beneficial for, say, IBM versus Rigetti?
So you can submit to both, and I guess check the results. As far as we do have some access, some unique access to some of their like air simulators, noisy simulators, namely Quera. So you could use that to test different modalities, but we don't actively compare systems. So that would, but yeah, it's easy to submit to different quantum computers. I just chose Anka 3 because I know it's never busy, but yeah, I could run the same circuit on a different quantum computer and check the results if they're online. They're not online all the time. So yeah.
Thank you.
Do you have experience which one is better, or can you?
So there's also different prices for these. So
price is a factor.
So that's a factor as well. IonQ, for example, costs more, but generally has better fidelity than Rigetti. IonQ has all-to-all connectivity, but it is much more expensive. I think about an order of magnitude more expensive.
Wow.
Shot. Yeah, so this is all things you have to take into account, whether you really need that extra connectivity or fidelity for your use case.
Mm-hmm. Okay, any more questions?
So
yeah, Thomas.
I'll try to speak loudly. Yeah, it's very interesting. Is the so it's a follow-up question actually from the previous one. When you showed your demo, it was only the result was only a very simple, set of numbers. Is it possible to extract more information on the computation or to get an insight in what the computer is doing?
So like
I don't know, maybe more statistics or
well, you can do different
how long it took
circuits or how long it took to return it. I don't think that is usually provided from these quantum computers. But yeah, you can always run more complicated circuits or yeah, I don't know if there's more information than just the measurement counts that comes back. I think there might be some extra metadata depending on the provider, but I don't know exactly what that is for each of them offhand.
Yeah. Okay, yeah, thanks.
Okay. Any more questions? Online, in person? If not, thanks James for the amazing talking.
Thanks for having me.